Hi, welcome to this final video on ensemble methods. This final video would conclude our understanding of ensemble methods. We conclude this by hands-on exercise on a data set which I have chosen. Um, what we would do on in this hands-on exercise is to try go over all the concepts we have covered so far. So just a quick recap. Ensemble methods are methods by which we take multiple models and then combine predictions from each of these models, and we saw how powerful it is. So combination the the entire notion is centrally rooted around the belief that a group of algorithms working together would outperform any single algorithm. So, with that being said, here is the data set. We would work on German credit risk. The original data set contains 1000 entries and 20 categorical attributes. This was prepared by Professor Hoffman, and this is data set on German people who would have taken loans from German banks, and then it has an attribute marking whether that person defaulted or not. Now, the original dataset is almost impossible to read because they have used quite a lot of symbols, and it has its own syncrasies very specific to German language. So, we are going to use a modified version of it. You can read more about the data here, and let's begin. We start by importing our usual data set, usual libraries. I import NumPy for my data frame operations. I import pandas for array and vectorized calculations. I import matplotlib, the visualization library, and percentage matplotlib inline to render all these graphs inline. I import Seaborn. This is another visualization library. From sklearn.model selection, I import test train split. This is to split my data into test and train data sets. I would import decision tree classifier from sklearn.tree. I would import this entire tree because I would want to use random forest and certain other classifiers for boosting and bagging demonstrations. So instead of importing them individually like this, I have imported the entire tree. I import metrics from sklearn because I want to calculate accuracy measures for each of my model. Now these two libraries are helper functions which you might not need actually. So let's take these off. So I've saved this dataset as usual at the same location in my ML Bootcamp GitHub repository in the data folder. I'm reading it directly from there. Let's see how this data looks like. Now when you're reading from GitHub repositories, because it's not reading from your desktop or from your stored drive, it is directly going to a GitHub repository and pulling the data. It might take a little longer than usual. However, here the data is. So we have some columns. These are series of attributes. It gives checking balance, month loan duration, so the duration for which loan was taken, the balance in the checking account of the person, the credit history, purpose of the loan, the amount of loan, savings balance, so this might be the balance in their saving account, employment duration, percent of income, years at residence, age, other credit, housing, existing loans count, job, dependence, phone. These become the features, and this becomes the target default. It's written yes or no. So straight away some things jump out. I see quite a lot of these columns having some missing data, and in this case, instead of just putting this as missing, as often you would see in most of datasets, it's it's filled by something else. Like in glass dataset we saw, it was in one of the datasets previously, not the glass dataset. I can't remember, but one of the datasets we worked on, it was substituted with 0. Pima Indian diabetes dataset, where blood glucose levels, all those measures, blood pressure levels were 0. Here, it's unknown. And second thing that jumps out is quite a lot of this data is text. So we need to work around these and then see how we can then start using this onto our model. Let's see how big the data is. So data has 1000 points, 1000 rows and 17 columns, 16 features, 1 target column. I use data.describe. You would see that describe takes only the numerical attributes. So we have only 1 2 3 4 5 6 7 numerical attributes of the 16. So that leaves us with 9 of these columns which are non-numerical, which we need to work on. So this gives me a fair indication of the distribution of this data, and nothing seems abnormal. Loan duration, so if this is in months, then a mean of 20 months looks fine, minimum 4 months, maximum 3 years, it looks fine. Amounts, nothing looks abnormal. Percentage income looks fair. Years of residence is between 1 and maximum of 4, it looks fine. Age, also nothing looks abnormal. We have a mean age of 35, minimum age of 19 and maximum age of 75, so this also looks fine. Existing loan count should not be abnormal. Yeah, minimum 1, maximum 4, so this also looks fine. Dependence 1 to 2, this also looks fine. So my numerical data looks fine. Let's see what's with the non-numerical data. So we have this bunch of columns which are in text as text objects. Now we need to convert these text objects into numbers somehow, and while converting it, notice there is certain order to these. So checking balance and savings balance, so these of course this is German bank, so all the denominations are in Deutschmark, so DM. So you would see there is some inherent order in this data. So less than 0 is somewhat lesser than 1 to 200, which is lesser than something perhaps greater than 200. So if you see here, less than 100 should be given a value lesser than 100 to 500, which should be given a value lesser than 1000. So there is some order as compared to some of the other text data like purpose. You have no reason to believe that there is any order. So a car can be assigned any number, education can be assigned any number, there is no order to it. So what I'm trying to say is, while it's okay to convert this into a number, we need to keep in mind and we need to be aware of the order. So if when we are assigning numbers to these, this should get a lower number than this. Same way, this should get a lower number than this, which should get a lower number than this. So if we are representing them as 1, 2 and so on, this should get a 1, this should get a 2 and this should get a 3. And that way, even though we convert this into numbers, we preserve the order in it. But the same doesn't go for these kind of the kind of columns that the purpose is. We have no reason to believe that there is any order. So a car can be 0, 1, but if we put 2 for furniture and appliance, that makes it twice as important. So we would first segregate the columns which are text in nature but has some inherent order, and we put numbers to those, retaining the order, and then we take the columns which are textual in nature, and instead of putting a number, we would one hot encode these. So label encode these, one hot encode these, and rest of them we let it be. There are multiple ways to treat unknown. One way is to drop all of these, second way is to impute. A third way, which we haven't tried so far, is by denoting them as a separate label onto itself. So I'm going to show that technique today because we have already worked enough on imputation and dropping these variables. So let's learn something new. What I have done is, this piece of code would categorize all these data, all the columns with object D type. The way I have done is, I've iterated over each of the column and then I check if the column D type is equal to object. If it is, then I'm converting it into a categorical feature using the command pd.categorical. Let's see how it works. So you wouldn't see anything change on the dataset directly. However, what you would see if I do an info again is, you would see from the previous one where it was object, it has now changed to category. So internally Python recognizes these as different categories and would assign some categories to it. This line of code you can ignore. Okay, now let's work on these categories. So now that we have defined these as categories, we are yet to convert these into numbers. All we have done is, we have told Python that in this pandas data frame, these are not just random texts, but these are categories. Now we need to assign a number to these categories. The way to go about would be first to understand the categories and then to assign them. So I would read the unique values for each of these columns, each of the category columns. So what I've done is, I have taken credit data dot checking balance dot value counts. Value counts give me counts of each unique item in this column. So let's see what it does. Okay, so checking balance has a 394 number of unknowns, 274 number of accounts with less than 0 Deutschmark checking balance, 1 to 200 Deutschmark checking balance, 269 accounts, and 63 of these accounts have greater than 200 Deutschmark as checking balance. The next column was credit history, and this gives a count of credit history. There were 530 good, 293 critical, 88 poor, 49 very good, and 40 perfect, and so on. So how it helps me is, then I can use this to create a dictionary. In this dictionary, what I have defined is, I've defined first thing as a column. So in checking balance, this column, I want everything which is 0 less than 0 Deutschmark, everything less than 0 Deutschmark to be represented or replaced with 1. Everything with 1 to 200 Deutschmark, I want it to be represented by 2, and anything which is greater than 200 Deutschmark, I want it to be replaced with 3, and all the unknown ones I want to have a separate label. Usually it's customary to, it's not customary but it's usual to denote it with something totally different from the nomenclature we use anywhere else. So we denote it usually with -1. That preserves the order of other categories that we are going to encode, and it somehow makes these algorithms more efficient and the dataset more cleaner to work with. Same way with credit history, critical 1, poor 2, good 3, very good 4, perfect 5. It doesn't have any unknown variables in it. It didn't have anything unknown, so I need not encode it. Same way I've done. Now there is a column like job. Now with these type of columns, if you have a belief that for the prediction you are making, if this classification makes sense, so if you're trying to predict a default and you have a belief that unemployed people have lesser weightage than unskilled one, who have lesser than skilled one compared to management. If you have no such belief, then you can as well ignore this here and just put this for one hot encoding as I have done. However, if you have a belief that there is an order in these variables, you can always use this in this dictionary and take this off from here. So the machine learning way is usually to try both and pick the answer which gives the best accuracy. So that's a typical machine learning way. Having said that, we now proceed. I've created a dictionary which would replace all of these textual values with something numeric while preserving the order within the each of these columns. I've also segregated the columns which I want one hot encoded. Remember, these columns had variables which did not have inherent order, and hence I do not want to map them using dictionary. I want to one hot encode them. Now all I have to do is take the data and use dot replace and pass this entire dictionary. So replace would go to this column, find this and replace it with this. Go to this column, find this text and replace it with this value, and so on and so forth. And then I use pd.getDummies and I pass the data set and I pass the columns for which I want to get dummies. And if you see the data, so checking balance here, it got converted into, it didn't get converted into anything, but all the values which were earlier text in nature got converted to a number now, while preserving the order in the data. So 1 would mean greater than 2. So the first one was less than 0 Deutschmark. The second one was between 1 to 200 Deutschmark, and hence it gets a 2. So by converting these to numbers, we have preserved the order. That's very important in these type of algorithms. If data has an order, you need to preserve it for your algorithms to give good answers. If you don't, then perhaps you might still get a good accuracy, but that would be just a fluke or just by chance, and often results would be unpredictable if you don't retain the order, inherent order within the data. So let's check the one hot encoded vectors. Housing was one hot encoded. Here it is. So housing got converted to 3 encodings. So this would mean the housing was own. This would mean housing had other as a value, and this would mean housing had rent on its value. Let's quickly check that here. So it looks fine. This had rent, this had own, and this was others. First one was own, fourth one was other, and the third last one was rent. First one was own, second last one was rent, third last one was rent, and this one was others here. So it has encoded properly, while we might have increased the number of columns, but now our data is ready to be worked on. So as usual, I would first want to split my dataset into test and training part. I do this by creating an X variable with all the features and creating Y variable with only the target. I have taken a test train split of 30%, 70%. So test would be 30% of the data, train would be 70%. Wherever there is randomness in any algorithm, Python does allow you to choose a random state. As long as the random state is same, you will always get the same result. So if you remove this, every time the algorithm would run, you will get a different result because of the inherent randomness in the algorithm. So it doesn't depend which number you choose. As long as you choose the same number, you will get the same result. So it can be anything, need not be a specific number. So I've split this. Let's start by building a simple decision tree classifier. So as you saw, I've already imported decision tree classifier in my libraries. Here I've imported the decision tree classifier. I can directly use it. I fit the model on X train and Y train. Here is our decision tree, because decision tree also randomly splits, has some amount of randomness built into it. We would still provide a random state for replicability. The criteria by default is Gini, but this option also includes entropy, so you can replace this by entropy and see if it performs better. So let's see how this a simple decision tree performs. So I want to see how it performs both on training and testing. So I would use it to predict the train data, store the predicted values in ypred train. I would predict the test data and store the values in ypred test, and then I pass both of these on to dtree.score and metrics.classification report. So it shouldn't be a surprise that the decision tree has scored a absolute 100% on the training dataset, because we know that decision trees, when allowed to grow uncontrollably, would overfit the data and would almost predict everything correctly. However, the true worth of an algorithm is found by predicting the test data, on which we see the score being 0.69. So whenever you see a huge difference between performance of an algorithm on training compared to the test, it's often an indication of overfit, and hence a decision tree has overfitted. Now there is a way to plot these. You can use a tree.plot underscore tree and pass the model, which was dtree, as a parameter, and it would plot the decision tree. So it gives a lot of text on for each line, each split. It would give the Gini coefficient, the numbers where it has split, and the logic behind splitting. And at the end, it would draw a tree. Because it's a largest data set, you can clearly see, when allowed to grow, how complex our decision tree has become. So it has become so large that this text is almost unreadable. I have to zoom in quite a lot to read these. However, the purpose of this demonstration was not to read the data or the splits, but just to show how complex this tree is. So let's regularize these model. One of the ways we saw we can regularize or prevent the tree from overfitting is by limiting the depth of the tree. So let's try limiting the depth of our decision tree only till the 3 branches. So I use the same line of code but here I've put a constraint of max depth, which is 3, and I store this model in a variable called dTreeR, and I fit this on train, and then I again use the same code to predict on both training and test. If I run this now, so you see the training accuracy from 100% has come down to 75%, because the tree is not overfitting, it doesn't predict to 100%. But the good thing is it generalizes well. So when we try it on the training data set, you see a comparable score between training and test data set. So this is the test score, this is the train score. If these are comparable, then your model is good. It would generalize well. And overall, if you see the test scores, we had a test score of 0.69 previously, and this score, a regularized tree, we got a much better score of 0.74. And the tree doesn't overfit, so it would generalize well. We can also visualize this tree. This tree is relatively simple, and hence you get much lesser text, and the tree would look like this. So it had only 1, 2 and 3. It goes down only 3 levels deep, Yeah, yeah, the visualization would give you the Gini score, the values, the number of positive samples, negative samples in your overall samples. It gives the branching logic, etc. Now we can also we have a feature available with these model decision trees. If we use dot feature underscore importances, it would give a list for every column how important was that in branching. So if I use this and stack it next to the column names and convert it into a data frame, I get something like this. And if I sort this, I would get which was the most important factor while arriving at a classification mechanism. So our regularized decision tree tells checking balance was the most important predictor for a default, followed by months of loan duration and then the credit history. So not only can you run your models, you can also see which features are driving the decisions. So you can also visualize it as a crosstab. Okay, so I had stored the predicted values in ypred test. This would give a confusion matrix. You should be able to read these and arrive at every value in the classification report by yourself. Bagging. Let's see how bagging works. From sklearn.ensemble, I import a bagging classifier, and so bgcl is the variable bagging classifier. I instantiate a model with a base estimator. So this would be the stack of models. So my stack of models are going to be the decision tree. I'm using the same decision tree which we built above. And you remember I said in bagging the model would benefit if each of the models which are stacked together are as complex as possible. So we do not use a pruned tree, we just take the original one and we use 50 such trees. We use a random state and let's see how this performs. So I have fitted the model on xtrain, ytrain, and I've stored the predicted values for test in ypredict, and let's see how this works. We get a much higher accuracy score compared to our pruned tree. So this reinforces our belief that if we stack together multiple models, it would outperform any single model. So you remember, if we when we used a single model, we had a train score of 69, I think. Yeah, we had a train score of 69 on our unregularized tree, and with our regularization the model accuracy jumped to 74. But when we stack together a lot of these unregularized ones, now our score jumps to 77.3. So we have now moved from a single model to a stack of models. We stacked them parallelly to each other, bagging. Now let's try boosting. Now remember, in boosting I said it would be good if we allow our models to be as simple as possible. So let's try it initially with a complex model and see what happens. So I have imported Adaboost classifier from sklearn ensemble. I've created a variable to instantiate it. I've taken a base estimator of that complex D tree that we grew. I am taking 10 such models and I'm stacking them serially, because in boosting we stack these serially, and I fitted it onto the train data, and I use that train model to predict on the test. I've stored all the predicted variables in y. Let's see how the score comes. So you see this, though it performs much better than the individual model, but it doesn't perform as good as our bagging, as our parallel stacking does. That's because we have used a complex tree. So if I take a regularized tree where we chopped off, or we put a constraint of the tree growing only 3 levels deep, let's see if we can see any gain in performance. We do not see any gain in performance. In fact, it has degraded by a small margin. That is because our Adaboost classifier is expecting really simple trainers, so it's expecting very weak learners. So if we remove this and run this, Adaboost classifier algorithm will by default pick up a decision tree which is only 1 level deep, so it has only one branch. And then let's see how it performs. So you see the model accuracy jumped up straight from 68 to 74. That's a massive 8 percent change, and this is now comparable to the way our bagging has performed. Here, the way our bagging has performed, and this is what I've done here. I've just removed the base estimator and allowed Adaboost classifier to choose its own base estimator. It chooses a decision tree with one branch, and we see the accuracy score jump up quite a lot. Let's see how gradient boost works. So the code remains the same except for Adaboost. I've imported gradient boost classifier, and you see our gradient boosting on. If we leave this blank, gradient boosting also chooses a very simple learner as a base estimator. It's often a decision tree with only one branch. It has the same accuracy as Adaboost. As you will learn, a machine learning method usually involves trying everything possible and picking the model which gives best accuracy. So often you would use both of these methods and pick up what works for you. So having seen both the ways of ensembling a stack of models, let's create a random forest. Random forest adds one more complexity to it's same as boosting, as bagging, I'm sorry. Random forest is same as bagging with one additional constraint. So while bagging means we sample the original data set with replacement, create multiple samples, and train one model on each of these representations of data. If all of these training models, all of these learners are decision trees, and we put an additional constraint that at every branch of decision tree we put a constraint of the number of features it can look at. So our data set after one hot encoding had 29 columns. So if I take off, yes, so it had 29 columns, so 29 features. Out of 29 features, if I constrain the max features to be used only as 12, and we grow 50 such trees, let's see how this works. So for random forest classifier, I've imported random forest classifier from sklearn ensemble. I instantiate a model. I want 50 trees in my forest, and I want to impose a constraint that whenever there is a branching in each of the trees, only 12 of the available 29 features should be used. Let's see how our random forest performs. So you see, by far of all the algorithms we have used, random forest has outperformed every other algorithm. So with this we conclude our series on ensemble techniques. What we have learned so far is our supervised learnings, and we have completed linear regression, logistic regression, KNN, naive Bayes, and cart and decision trees. Until here we were using one model each time on a data set. Then we progressed to learning ensemble techniques. Within ensemble techniques, we learned how we can use multiple models together, and how it is that multiple models working together often outperforms performance of any single model. And then we learned two primary ways of doing this ensemble by stacking the models in a serial order, also called boosting. If we stack them parallelly, it's called bagging. One very specific type of bagging is random forest, where we impose even more constraints on it. The reason why we put more and more constraints is because we want each of these models to be as different from each other as possible, for our predictions when we take a vote to be as good as possible. So this concludes our series in ensemble learning. I hope you enjoy these videos and learn from it. If you do, then please consider subscribing and liking the channel. Thank you so much.